Good evening. Welcome to the show, if anybody is here. Sorry I had to post a new link within the last like 5 minutes. Of course, I like to get this thing up nice and early, put the title card up there, give people a chance to show up, and my computer just froze on me 5 minutes before show start, which is unfortunate because I was also prepping some notes at the last minute, and that's fine. So hopefully you guys saw the new link. I tried to post it everywhere, throw it all over the place as fast as I could, so people would know that the new link is now live. So the previous link I posted, dead link. It's just 16 minutes of the title card. This is the actual show, obviously, if you're watching this. But hey, what's up? I'm David. Welcome to A Thousand Shimmering Lights, my YouTube channel and my YouTube show. And I'm going to check real fast and see. Danielle, awesome. We've already got a viewer. Fantastic. We've got at least one person here. And let's see. Looks like, yeah. Looks like we just have one person so far, but that's all right. While I wait for some other people to get here, Danielle, can you let me know if you can hear me? Because I'm seeing in YouTube, it's saying the audio bit rate is a little slow. So I just want to make sure that the audio actually is coming through nice and clear for you. So if you or anybody else could just quickly say in the comments if you can hear me, that'll let me know. Robert says, howdy, what's up, Robert? Welcome aboard. We had a bit of a rough start because the computer just suddenly crashed on me before I was able to get the stream up, or while the stream was waiting to load. And now I'm just checking to make sure that the audio and everything sounds good. People are saying they can hear me. Zach's here. Excellent. Awesome. Well, we got some people here, and we are ready to have a show, so I'll go ahead and do the real intro. This is David. Also, bear in mind, if it seems like I'm rambling and I don't notice your comment at first, the stream is actually on a slight delay. So you guys are seeing me a little bit after I say what I say. And so I'm seeing now that you guys are saying that the sound is clear, but that's just because you guys are only just now getting what I was saying earlier. So that's why it seems like I don't notice it first. If you say something, or if I don't notice it first, your chat comment, it's because you're kind of in the future, I guess. Or no, you're in my past, I think. Anyway, time dilation is weird. We'll talk about time dilation tonight. So this is A Thousand Shimmering Lights, the only YouTube planetarium live stream where you are the planetarium director. Meaning that your questions and comments drive the discussion. I don't plan these things in advance. I just go with the flow and let people's questions drive the conversation, is what I usually say at the start of these videos. But tonight, we actually do have a plan. We do have a theme. Tonight is the Galaxy Season special episode. So this is the first time I'm doing a themed episode, and it is all about galaxies. So I'm going to let some people join while I continue to talk for a second, to do some of the intro stuff. I'm going to quickly, well, for one thing, I'm going to get one of my windows ready here. There we go. Okay. All right. So I'm going to quickly mention the Astronomy Club. I am a part of an astronomy club here in Jacksonville, Florida, called the Northeast Florida Astronomical Society. If you live in the greater Jacksonville area and you are an astronomer or you're interested in astronomy, definitely check us out. Our website is, oh my goodness, I'm not even on the logo right now. There we go. Our website is nefas.org. That is Northeast Florida Astronomical Society.org. And yeah, we are the Astronomy Club here in Jacksonville. We've got almost 200 members, and I am really hoping we break that 200 member ceiling by the end of this year. It would just honestly would just break my heart if I had that many members in this club. I think it'd be fantastic. Even if you aren't interested in joining the club necessarily, you should check out nefas.org if you live around here and take a quick look at our calendar. In fact, I'm going to take a quick look at it and make a couple of announcements about some upcoming events. So let's see here. Tonight's the 24th. Tonight, tomorrow night, and Saturday. And actually, I think these are daytime events. This is during the day, and during the day. We are going to be at the Jacksonville Science Festival setting up solar telescopes. So it is never safe to observe the sun through a telescope. You will damage your eyes permanently and painlessly. There are no pain receptors in your retina. But specialized equipment has been designed that can actually safely observe the sun using special filters that make it safe to view. And we will have telescopes at the Jacksonville Science Festival specially configured for safe solar observing. So I just really always emphasize anytime we do solar that under normal circumstances you will never ever ever want to point a telescope at the sun. But we are actually going to be using safe solar telescopes to observe the sun at this event. So if you come, let me get some information on that real fast. Let's see here. So that's at Metro Park. Here's the address for you: 1410 Gator Bowl Boulevard. I think it's hosted by UF. And it's 9 a.m. to 5 p.m. is the time span of this festival. There's going to be a lot of other people there talking about a lot of cool science stuff, and we're going to be there too. And then this weekend, some of us are planning on going out to our dark sky observing site. If you plan on joining us, just understand it is a very remote location. It is not an outreach event. It's an event that we do where we make our own observations. So we observe light discipline. That means we don't use any bright white lights. We just do red lights. And we highly recommend meeting somebody at the Firehouse Subs ahead of time. Best way to work that out is to get on Facebook and see people chatting about it. I'm going to post about it later. I always meet people at the Firehouse Subs in McClenny so they can follow me there because it's difficult to find. And then we got some events coming up next month as well. More observing next week as well, the following week. Board of Directors meeting. Let's see, what do we have here? The 9th, April 9th is our next Hannah Park event. That's our next big one. We're going to set up telescopes at Hannah Park. We do it every month. We got to get in before they close the gate, but right now, because of daylight savings, they're doing that at 7:30, so you've got some time. And then once it gets dark, I kick it off at the laser pointer show, not unlike what I do on here on YouTube. And then we have a whole bunch of telescopes for people to look through, and we'll check out the moon, planets if there are any, galaxies like we're talking about tonight, nebulae, all kinds of cool stuff. If you are interested in joining the club, of course, there's this membership tab, Join NEFAS, and you can just fill all this out. Memberships, these are yearly memberships, so for students and seniors, $20, individuals, $40, family, $50, and then benefactor and corporate are for people who want to sponsor our club and give extra. That just about covers the quick announcements I want to make about the club, because I just like to let everybody know about it, and I am the membership director for the club. Somebody says, Swamp Saturday, see you there. Yeah, I'll see you there too, dude. I'm definitely planning on going. So yeah, I'm our membership director. If I didn't promote the club and encourage people to join, I wouldn't be doing my job. Well, we have 10 viewers according to YouTube, which is fantastic, and we're only just getting started. So I'm not going to squander this wonderful audience I have tonight. I'm going to go ahead and get talking. So we're going to talk tonight about galaxies. Actually, I'm going to bring this back up here. We're going to talk tonight about galaxies, and I'm going to start off, I love telling stories, so I'm going to start off telling it as a story. And we're going to talk about how we went from knowing nothing about galaxies to our current understanding of galaxies. So I'm just going to pull up a nice picture to have in the background while I talk about it. Which picture do I feel like really does it justice? This guy, I guess. This one looks cool. Can I make it big? Make it big. There we go. Whew, that's taking a second to load. Man, you can tell I'm eating up all our bandwidth right now. Okay, so there we go. Got a nice picture of the Milky Way. So I want to start off talking about ancient Greece, right? So, of course, way back in the day, our ancestors didn't have nearly the light pollution that we have today. The way you lit your home was a candle or whatever they used, lamps, that kind of thing. And at night, most people blew those out and went to bed. So if you were awake at night and you looked up, you could see the stars, right? You could see the sky, and you could see all these wonderful things that we don't get to see here in Jacksonville unless we go out somewhere dark. Well, ancient people didn't know what a lot of this stuff was, but you can't help but look at it every night, and it's beautiful, and it's inspiring, and so they name these things. The constellations obviously have names, but to the ancient Greeks, they looked up and they saw this stream of this glowy patch in the sky, right? So if you look up in the sky, there's a line across the sky that's brighter than the rest of the sky. at nighttime, right? So if you look above it or below it, it's a little dimmer. And if you've never had a chance to actually see it for yourself, it doesn't quite look like this picture over here. This is a long exposure photograph that's really bringing it out, but it does still look like there's like almost like a bright glowing cloud that stretches across the sky. Um, and so the ancient Greeks gave it a name and they called it Galacticos Kyklos, which means the circle of milk, the milky circle. Because right away they figured out that it's a circle around the Earth, right? Or that's what they thought of it as, is a circle around the Earth, sort of a milky, it's not as dark as the rest of the sky. And that word, Galacticos, is actually where the word galaxy comes from. So I think probably the first fun fact of the evening is that the word galaxy is derived from the Greek word for milk. Uh, in fact, one of the sugars found in milk that's a component of lactose is called galactose, right? So galaxy comes from a word meaning milk. Fun fact. Okay, so fast forward a little bit. The Greeks also figured out that some of the stars don't move with the rest of them. They seem to wander around. They called them wanderers, or the word is planetae, and that's where we get planets. And then moving into, say, more like the Middle Ages and that kind of thing, we have Galileo, who I actually had to look up what the actual year was, but Galileo was one of the first people to start using a telescope to observe the sky. And one of the things Galileo was trying to prove was that the Earth and the planets go around the sun. So prior to Galileo, this guy named Copernicus basically said, well, we've always assumed that everything's going around the Earth because we look up and we see everything and we just assume we're in the middle. But the math actually works better. The planets' orbits are more predictable if you put the sun in the middle and have the planets going around. And then this weird habit of planets to go backwards sometimes is solved because we just catch up to them in our orbit. So Galileo is working on this problem. So is Kepler and Tycho. But Galileo does something that nobody else had done yet, which is to get a telescope. So telescopes started off as something called the spyglass. And I'll pull up a picture of one of those for reference. Here we go. This is something like what Galileo would have had, right? Something like this guy. It's the spyglass. You guys have seen the classic spyglass. And it was kind of a hot new thing in Galileo's day. It was basically made for sailors, right? They'd use it to spot land. And Galileo figured, well, if you can see further with this device, and if the things in the sky are obviously far away, I'd like to get a closer look at them. So Galileo starts pointing his telescope up at the sky. And, very famously, we know about his observation, 1610, somebody posted in the chat. Thanks, Zach. Very famously, we know about Galileo's observations of the planets, right? He saw that things are going around Jupiter, Venus has phases, and he basically provided some evidence and support for the heliocentric model, that the planets and everything are going around the sun. But Galileo also tried pointing his telescope at some of the fuzzy things in the sky. And one of the things he figured out is that you see stars through a telescope that you don't see with the unaided eye, that you see more stars. So he pointed at the Pleiades, which usually you can see about 6 or 7 stars. That's why they call it the Seven Sisters. He found that there was a bunch more stars around the Pleiades, right? He pointed at the head of Orion, which normally looks like 3 stars. There's a bunch more stars there. And one thing he did was he pointed the telescope at the Milky Way and found that the Milky Way is actually made up of stars. He found that when he looked at it more closely, this sort of milky, blurry part of the sky was just thousands and thousands of stars. My channel name is actually a bit apt because what he saw was 1,000 shimmering lights, right? He saw all these stars across the sky. Everywhere you look in the Milky Way, you resolve just a sea of stars, right? So that was a big breakthrough. Galileo figured out that the Milky Way is made of stars. And so astronomers in the time since Galileo learned a bit more and more about our universe and started to piece together that it seemed that the stars of the universe, as they knew it at the time, were concentrated across this narrow band of sky, right? And the most obvious explanation for why that is, especially if we're not in the middle of the universe, is that we must be embedded inside of a flat disk of stars, such that when we look through this disk from within, it forms a straight line across the sky. Or if we chart it throughout one full revolution of the Earth, it completes a circle all the way around us. We see it in every direction, right? Winter, spring, summer, and fall. A little bit later, I'm going to get into how it varies throughout the seasons, but nonetheless, we do see it in all seasons. So this Milky Circle is actually a flat disk of stars that we are embedded inside of. Okay, now we're going to move forward a little bit to the 1700s, and we're going to talk about a guy named Charles Messier. Messier didn't make any special discovery in this, but he's an example of the kind of things people were talking about at that time. So this is Charles Messier. And in Messier's day, we knew about the sun. We knew about the planets. We knew that we were embedded in a big, flat, swirling disk of stars. And we knew that there were blurry things, because there were things that if you point your telescope at them, they're still blurry. And we knew about comets, right? And one of the things about comets is that they are also blurry. So a comet is a big chunk of ice. It moves close to the sun, and all that ice turns to steam. It actually skips the step of melting and just goes straight to steam. The sun, the solar radiation, all that stuff coming off of the sun, pushes that steam away from the comet and forms this tail behind it, and that's what a comet is. Only the best and brightest comets become visible to the unaided eye. A lot of comets just remain little blurry things that you have to look at through a telescope. And the sort of the hot thing in Messier's day was to try and find comets. And that's what Messier did. He was a big comet hunter. And he found a bunch of these blurry things that never moved, right? Because the thing about a comet is, because it orbits the sun, if you look at it night after night after night after night, it should move relative to the background of stars. And he found ones that didn't. And the word that people had for these blurry things was nebula, which comes from a Latin word meaning cloud, right? And even in modern English, we sometimes use the term nebulous to mean vague. There's literally, like, it's a vague thing. It's a blurry thing. We don't know what it is. It's some kind of blur. Messier is actually my favorite example of the sort of discoveries and blurry things of his day, just because he made a whole list of things that weren't comets, and basically was like, these aren't comets, don't bother looking at them. And a lot of the example galaxies I'm going to show you guys tonight are on his list of don't bother looking, it's not a comet. Of course, now we know what they really are. But so now our picture of the universe is sun, planets, lots of stars. At some point, people figured out that the stars are probably also other suns, that the sun is a star. And there's blurry things, right? There's these blurry things, we call them nebulae. Eventually, astronomers figured out that these nebulae are big clouds of gas. But people started to notice that some of these nebulae had an interesting shape. So the term started getting thrown around. People started talking about spiral nebulae, right? So I'll give an example. Spiral nebula. See if Wikipedia has a... Yeah, so here we go. I figured I'd get some cool stuff. Right, so this is somebody's sketch of one of these spiral nebulae. Somebody sketched this by hand. And they said, hey, one of these blurry things, now that we've got bigger, better telescopes, it's shaped like a spiral. What's up with that? And moving into the early part of the 1900s, the 20th century, people didn't know. And so even as recently as the 1920s, we thought that the Milky Way, that flat disk of stars that we're embedded in, was the whole universe, right? And so the universe was mostly a flat disk of stars with some stuff above and below, and these nebulae, these blurry things. But some of the astronomers in the 1920s started to suspect that there was a reason why there seemed to be this tendency for some of these blurry things to just be all kinds of weird blobs, but for some of them to be a particular spiral, right? Why is that? Why do we have so many of these gas clouds that form a spiral? And there was a lot of debate amongst astronomers. Some astronomers said, well, as the matter's pulling in, it naturally forms a spiral, which makes sense. And they said, well, so there's just gas clouds that are spiral shaped, and it culminated in something called the Great Debate. Oh, sorry, I skipped a bit. There were other astronomers who started arguing that maybe our own big flat disk of stars that we thought is the whole universe is also a spiral shape. Because if you were inside of a spiral, that's what it would look like. It would look like a flat disk, right? If it's a flat swirling spiral. And if that's the case, maybe all of these spiral nebulae, as people were calling them, are actually other big flat disks of stars like our own, like what we think is the whole universe. And so the term started getting bandied about where astronomers were calling these things island universes. There was the island universe hypothesis. And there were two big astronomers named Shapley and Curtis that really were arguing these two points of view. Shapley argued that the Milky Way was the universe, and that these spiral nebulae really were just nebulae that were shaped like spirals. They were just gas clouds that happened to be spiral shaped. Emily says so they were seeing other galaxies and calling them nebulae. Yeah, that's exactly right. In fact, if you look up some of the really famous galaxies, you'll sometimes still see the term nebula in their name. So the Andromeda Galaxy in some old books is called the Andromeda Nebula, or the Great Nebula in Andromeda. Bode's Galaxy is sometimes called Bode's Nebula. The Whirlpool Galaxy, which is actually what this is a sketch of, is sometimes called the Whirlpool Nebula. And I want to give a little bit of credit to the guys who are arguing that the Milky Way is the whole universe, because I think sometimes when we communicate science and we tell the stories of the history of science, we often present this narrative of the closed-minded establishment who were foolish and the brave rebel who figured out the new thing. You know, like Galileo's story is the perfect example of that, right? Galileo having to fight the church and the whole thing. But the reality is that a lot of times in science, the establishment has a reason why they think this is the case. And sometimes it's hard to overturn what was established, not because people are just being hard-nosed or whatever, but because they have good reasons to suspect what the current model is, to think that the current model is accurate, and you have to present really good evidence that it's not. And so I think we need to give credit where credit's due when we look back at some of these old things like the Great Debate. So I actually looked into it a little bit and looked at what were Shapley's reasons for resisting this idea that these are other galaxies. Well, for one, in science, we don't just want to say that A is B because A looks like B, right? We want to make sure we have really solid proof that there actually is a relationship there, right? We don't just reason by analogy. We want to make sure we are being accurate. And so Shapley would be correct in saying just because this thing is shaped like a disc and the universe, as we understood it at that time, is shaped like a disc, doesn't mean that they're the same thing, right? Because a protoplanetary disk, that big disk of dust and material that eventually becomes a solar system, it's disc shaped, but that's not the same thing. When we see protoplanetary disks, they really are part of our galaxy, right? But Shapley had a couple other points as well. One of the arguments that Shapley made is that if you take a galaxy and you look at how bright it appears to be, and you figure out how bright it would be based on its distance, that the galaxies have to be outrageously far away to be an independent thing, to not be part of the Milky Way, right? Because light, if you shine light, as light travels through empty space, the brightness falls off over distance. It's really bright at the source, it gets progressively dimmer. And there's the law that describes that is called the inverse square law. It falls off as the inverse of the square of the distance. You can calculate that. So you can apply that law in reverse, and you can say, okay, so let's say that the spiral nebulae really are galaxies just like ours. And we look at, say, the Andromeda Nebula, and we say, okay, well, it is a certain brightness. It's fairly dim. It's compared to some of these other nebulae in our own galaxy, it's fairly dim. Certainly compared to the independent stars that we see in our galaxy. So if this thing really is a swirling ball of stars, and it appears this dim, it has to be like 10 to the 8th light years away. And sometimes when you're working a problem and you get a number that is just unbelievably huge, that is way beyond. Cooper's watching. Awesome. Welcome, Coop. Uh, if you get a number that's just way beyond the pale of anything you've encountered, that sometimes is a sign that maybe you're going in the wrong direction. And so Shapley argued that if we accept the island universe's hypothesis, then what we consider to be the actual universe is unbelievably huge, right? By orders of magnitude huge. And that's a really big claim. So that needs really solid evidence. How do I commit? I'm not sure. I'm not sure I understand the question. How did I commit? Um, if you want to clarify, I'm happy to come back to that. So, uh, it and okay, I'm watching the stream as well just to make sure, and I started moving again. I thought I saw it freeze. Okay, so uh, yeah, so Richard mentioning Galaxy Season, and I am definitely going to get into Galaxy Season. That's actually the point of the conversation tonight. And I apologize for monologuing more than usual. Uh, oh, two devices. Oh, how did you comment? Okay, I think Karen commented, and so did Cooper, and she was like, "Wait, how did you comment?" Because she didn't realize you could be on two devices. I'm with you now. Okay, cool. So Karen and Cooper, they're club members of the astronomy club. Great kid and a very very supportive mom who I really appreciate. She does a lot to support Cooper's interest in the hobby, and Cooper is a really cool kid, and he's really getting into this stuff. So I'm glad they're both here tonight. So yeah, I was talking about Shapley, right, and his arguments. Another argument is that Shapley knew another guy, and I forget his name, and I had it in my notepad before my computer crashed, Van Marin or something, who thought that he had observed the or the pinwheel galaxy rotating. So he claimed, and we now know he was mistaken about this fact, but he thought, sometimes you think you see things, he thought he had seen the whirlpool rotating. And if he had, the argument was that if it were as far away as the island universe side of this debate was claiming, it would have to be breaking the speed of light because of how big it would be at that distance, and yet rotate at the velocity that he thought he observed it. It would have to literally break the speed of light. And so, also I just realized I was taking my hand like out here someplace. I should be here doing the rotation. So those were some of the arguments in favor of the Milky Way really is the whole universe. And they really did have some good points. Shapley's argument had to do with observing the Great Nebula in Andromeda, as it was called at the time, and saying that they had observed too many novae in it. So a nova is basically a star blows up, right? So a star, there's a couple of different ways that this can happen, and we now know that there are lesser events called novas or novae, which is where a neutron star gathers material until that buildup causes a detonation and that lights up. And then there's a supernova, where a massive star detonates completely and destroys itself. And Shapley had actually observed a supernova in the Great Nebula in Andromeda. They saw a star light up, and it was brighter than the whole galaxy put together. And again, he reasoned that that would be impossible if this were an object way, way, way out there, and that was a star blowing up that was actually a part of that object. He said that would be, there's no way it could generate the energy to glow brighter than its host galaxy. Uh, and Emily says it's surprising they knew about galaxies as early as the 20s. See, to me, when I was learning this stuff and doing my research, it felt late. But that is kind of interesting. But yeah, so this is the debate going on in the 20s. Um, yeah, it seemed like when she was a kid, galaxy and universe were interchangeable. I feel like some people still use them almost interchangeably. And in the 20s, they certainly were. because we thought the universe was our galaxy. But yeah, so there was that other argument about the nova. Well, Curtis said that in his observations of Andromeda, he had noticed several, not of the big bright kind, but several novae going off in Andromeda, and that the rate at which they were happening, there was more novae happening within Andromeda than within our entire galaxy as a whole, right? Which doesn't make sense, right? He was basically saying like this thing has more stars popping than we see in the whole galaxy. And then the other thing was that some people had noticed that if you look in the region of the what we call the Milky Way, you don't see any spiral nebulae. You have to look above or below that big bright line of stars to find spiral nebulae, right? Talk about the outside of stars of a galaxy rotating at the same rate as the inner stars. Yeah, that's another thing, and we'll get to that in a second because that touches on dark matter. So, Curtis was basically saying and was saying if these things are part of the Milky Way, they should conform to that band. We should see more of them there than elsewhere. But actually, the opposite is true. There was an exclusion zone, they would call it, where you see much fewer galaxies in the Milky Way part of the sky than you do above it or below it, almost as if they're unrelated to that disk. And in fact, we also know that this is partly due to the fact that there's gas in our own galaxy, thick clouds of gas, that when we look through the galaxy, that gas dims the light of anything behind it. And so we can't observe any galaxies that are behind our own. Our own galaxy gets in the way of us seeing them. And that creates what's sometimes called the exclusion zone, right? You have to look perpendicular to the disk that we live in to see the other disks, right? So these are some of the arguments going on about this during what's called the Great Debate. And this debate was actually settled. I think there was an actual debate. They sat down and had like a structured debate, and I think Curtis won. But generally speaking, Edwin Hubble is the guy who settled the issue definitively. Right? Here he is, smoking a pipe. This is Edwin Hubble. And I honestly think Edwin Hubble's name deserves to be right up there with Galileo, with Kepler, with Copernicus, in terms of completely revolutionizing our understanding of the universe. What Edwin Hubble did was he found a way to settle for once and for all just how far away these spiral nebulae are. And so let me explain what he figured out. So there's a kind of star called a variable star. And basically the short version is a variable star is variable in its brightness. It gets brighter and it gets dimmer, right? Now, we can't tell how far away any given star is. Not really. Because if you see a star and it's a certain brightness, it could just be a really bright star. Some stars are brighter than others. Or it could be closer than another star. You really don't know. But some stars are close enough to our own sun that as we orbit the sun, their position appears to change slightly from our perspective. That's called parallax. It's the same thing as when you go down a road and the nearby telephone poles are just whipping by, but the house in the distance, is sort of slowly crawling along. Well, we can observe that with some of the stars, provided they're close enough. Okay, so now we know how to find out how far away some of these stars are. Well, using that trick, some stars were identified, and we knew how far away they are. And once you know how far away a star is, because you know the inverse square law, you can figure out how intrinsically bright is it. How bright is it actually, not how bright does it look. And there's a class of stars called variable stars that the brightness actually shifts. They get brighter, they get dimmer, they get brighter, they get dimmer. And some of them are random, and some of them have a pattern. But there's a particular kind of variable star called a Cepheid variable star, where it's a very predictable pattern of bright and dark and bright and dark. But what's interesting is the brighter the average brightness of that star. So if you take its brightest and its dimmest and you average them together, the higher that number, the longer the period between brightening and dimming, which means that the pattern, this sort of frequency of dimming and brightening of the star, is directly tied to how intrinsically bright the star is. Which means if you find one of these, no matter how far away it is, all you have to do is time it. Observe it, count the days for it to get all the way as dim as it can get, count the days for it to get as bright as it can get, do a little math, boom, you know exactly how intrinsically bright this star is. And since you know the inverse square law, you know how far away it is. And this was a breakthrough because it meant that there was a class of star that exists in the universe that no matter where it is, no matter how far, if you can observe one and just keep track of its brightness, you know how far that star is from the Earth. So Edwin Hubble found some in the Andromeda Nebula and other spiral nebulae and tracked their brightness and did the math and found out that they were, X brightness, and this is how intrinsically bright, this is how bright they look, did the math. Holy cow, they are way out there, right? He figured out that the Andromeda Nebula is 2.5 million light years away, and this settled it. That's another galaxy. That is not part of our galaxy. So Edwin Hubble is the reason we know definitively that the universe isn't just a big flat disk of stars with some spirally looking nebulae inside of it, but that big flat disk of stars is just one of a whole class of gigantic objects in space. And that is where I wanted to start off the talk, is given the big history of galaxies. I'm going to pause for a second and take a look at the chat and see if we've got any questions or anything in the chat before moving on. And Edwin Hubble discovered some other really cool things about galaxies as well that I'm going to talk about. But even with the theme tonight, I don't just want to monologue all night. I want to give people an opportunity to take part in the conversation. Let's see. Yes, we've got that comment about it felt like back in the 80s people were saying galaxy and universe interchangeably. It definitely is the case. Sometimes we have to also draw a distinction between the way we use words scientifically, where every word has a very particular meaning, and the way words are just sort of used commonly, right? So people talk about, the universe, the galaxy, or whatever, and it just sort of goes in this general blob of space stuff. But if we're scientific, these words have particular definitions and they refer to specific things. The universe is all of physical reality. Galaxy is a thing in that physical reality, right? Let's see here. I'm also checking Facebook because I know that not everybody has YouTube, but some of my friends on Facebook will sometimes Facebook message me questions and things that they might have as well. Got a comment saying, wow, that's awesome. I think it is. I think it's brilliant the way Hubble figured out how far away these things are. And other things besides. So somebody had mentioned in the chat, talk about somebody said talk about the galaxies rotating, and then Zach just asked if Cepheids have a variable brightness, how are they used as a standard candle? And it says, and then he says, sorry, I missed it. That's okay. I don't mind reiterating. So the reason why a Cepheid can be a standard candle is because it's actually because of the fact that they vary in brightness. I'll go ahead and pull up a chart that I think will actually help illustrate this. I found it on the Wikipedia article about Cepheid variables. Cepheid variable. Okay, so here's an example of one. This chart right here. So the blue line is tracking classical Cepheid variables, and then there's actually something called a type 2 Cepheid, which is this green line. But the left side here is the absolute magnitude. This is the actual brightness of the star, not how bright it appears to us. And magnitude is kind of like earring gauges. The smaller number is actually brighter. So we see how these numbers are getting negative. That's because if you were next to it, it would literally be bright like the sun or brighter than the sun. So it would be a negative value for magnitude, because lower is higher. Don't let that throw you. So that's what's being tracked on the left-hand side of the chart. On the bottom part of the chart is the periodicity, meaning the time between dimmest and brightest. How long is that period for each of these swings? And you'll see that as the period increases in days, the brightness increases as well. And you see how the line bends like this? This is a logarithmic progression. It sort of It approaches but doesn't quite hit zero on one end, and then it starts to level a little bit as you go up, but never quite levels off. So if you're timing a Cepheid variable and you look at it and you go, okay, I tracked it for a while and I saw it, the dimmest it can possibly get and the brightest it can possibly get, and the time between the two was about 30 days. Well, you know that the intrinsic brightness, how bright the star actually is negative 5.2 ish. And if you know that, then and you know the inverse square law, you know the rate at which it dims, because you say when I look at this star, it's fourth magnitude, right? But if I were next to it, it would be negative 5.2. Run the math. Oh, it's fill in the blank light years away, right? That makes it a standard candle. In astronomy, the term we use for stars or measurements that can be used to determine how far something is called standard candle. And actually, I've grossly simplified the subject. There's a progression, like a ladder of standard candles that are used in astronomy, because at the face of it, the problem is impossible. You can't tell how far a star is. You cannot differentiate that. But nearby stars, we can tell the parallax. By doing that, we figure out how far some of the Cepheid variables are, and we learn this relationship. Now that we know that, we can use the Cepheid variables to find things that are further away, knowing that if they're in a cluster, the other stars in the same cluster are the same distance, we can figure out there. And so there's like a chain that you can go through and solve the problem, where if you just took that star on its own, you could never know, right? And every one of those different methods is called a standard candle. And so Cepheid variables are an example of that. Let's see, checking the comments again. So that's the answer to the question of how Cepheid variables function as a standard candle and allowed Edwin Hubble, I should say. I say us like I was in the lab with him. Allowed Edwin Hubble to figure out that the universe is actually incomprehensibly huge. That Shapley's objection that the universe couldn't possibly be that big, it really is, and it is mind-blowing how huge the universe is. It's difficult to wrap your head around how big, just absolutely how vast the universe is and how far away these things are. So let's talk for a second. We're talking about Edwin Hubble. We'll talk about a few more things. Edwin Hubble taught us a lot about galaxies. He kind of made galaxies his whole thing. Another thing he discovered is something called redshift. So when he analyzed the light from these distant stars, he discovered something called redshift. And I'm going to go ahead and see if I can bring up. Yep, we're getting a lot of stuff that has nothing to do with astronomy here. Stellar redshift. Okay, we're getting warmer. How about we just go with stellar spectrum? Here we go. Okay. So this is a great chart. This is the one I'm going to use. All right. So if you take the light from a star and you break it up into the whole spectrum, you know how you can use a prism to make a rainbow, or even if you just spray water in the air, that the little droplets will make a rainbow. That's how we get rainbows. All right. So if you take the light of a star and you do that, you get the rainbow. And when you're looking at the rainbow, you'll see these black lines that occur in the light from that star, right? So what these are is they're the absorption spectra for certain elements, right? So we know that if it has this big black line right here and this one over here, that element is helium, right? If we see there's a line over here, it's really hard to see in the red. Then we have here and out here, here. That's associated with hydrogen. This line here in the blue, that's associated with carbon, right? This one here in the green with these guys, that particular pattern is iron. Every element has a unique fingerprint. This is actually how we know what the stars are made out of, right? You can tell by looking at the lines, and by looking at the intensity of the lines, you can get the amounts of the elements that are in the stars. So that's cool, and scientists knew about that in Hubble's day. What Hubble discovered, once he knew how far away these spiral nebulae were, he found that there was a correlation between how far they were and where these lines appeared in the spectrum. because you would find the exact pattern that you're looking for hydrogen, right? So you got this guy down here, this one, this one, this one, this one, right? That exact pattern was slid over towards the red side of the spectrum from where it should be, right? It's the right pattern of lines, but they're not where they're supposed to be. They're the wrong colors. They've slid over, right? And he found, and a tiny amount. I'm exaggerating with my hands, but it's a small amount. But he found that the further away something was, the stronger that effect, right? Now, if you've ever been outside and an ambulance goes by and you hear the siren going, meanie, 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 and the pitch drops as it goes by, right? You've experienced this. Somebody's going to take that clip of me making that noise and it's going to go viral and I'll never be able to show my face in public again. But that effect that's happening where the pitch drops is called the Doppler effect. And that's because as the ambulance is moving, it's putting out pressure waves, sound waves in front of it, but it's moving at the waves it's making, so they bunch up. And as it's moving behind it, it's running away from its own waves that it's making, so they stretch out. Longer wavelengths are a lower pitch, shorter wavelengths are a higher pitch, right? So, with light, shorter wavelengths of light are blue, longer wavelengths of light are red. If an object is moving at a significant enough fraction of the speed of light, then we can actually see that those light waves stretch out behind it as it moves and bunch up in front of it as it moves, and that shifting tells us that the object is moving, right? So if something's moving away from us, the light should have shifted towards the red end of the spectrum. If it's coming towards us, it should shift towards the blue end slightly. You wouldn't like look at the star and go, man, that star looks blue or that star looks red, unless it's outrageously far away. But you would notice it when you're analyzing the spectrum like this, right? You would find the fingerprint, but slid to the wrong place. So Hubble noticed that these distant galaxies are doing this, and the further away, the stronger the effect. And what that must mean is that everything is running away from everything, right? Because if it was shifted, but they were all shifted the same amount, then they're all running away from us at the same speed. But if it's the case that the effect increases with distance, that the further things appear to be running faster, then what it really is everything is running away, and the further away something is, the more that combined of us and them running away adds up to make it look like they're really going fast. And that's my best attempt to explain it, because the redshift really throws a lot of people and makes it sound like we're in the middle of the universe. We're not. So this is how Edwin Hubble figured out that the universe is expanding. Actually came up with something called the Hubble constant, which measures that expansion. And figured out that the universe not only is enormous, but is also growing. It's actually expanding over time. Another thing Hubble did, and this is actually one of the other points I wanted to get into tonight about galaxies, so I'll go ahead and let this be a transition, is I wanted to talk about the types of galaxies. So we've talked the history of galaxies. Edwin Hubble also classified them into types based on their shapes. So we're now getting into the part of the discussion tonight, which is what do we know about galaxies? What can we learn about them? So we've learned about the history of how we figured out what they are. Now what are they, right? So galaxies come in a couple of different flavors. And I'm actually going to pull up, again, my man Hubble. I'm going to pull up his chart. Hubble Galaxy classification. I bet you this is exactly it. Yep. Okay. So leave site. There we go. All right. So Edwin Hubble came up with a classification system based on how the galaxy looks. And it's sort of like a tuning fork diagram here. So he noticed that some galaxies were just big balls. Big balls of stars. Big old, they don't have any particular shape. Because this is the thing, not only did he figure out that the spiral nebulae were far away, but he figured out that there was a bunch of spherical nebulae that were also really far away. Right? Huge leaps and bounds. I cannot overstate how big a deal Hubble's contributions to astronomy were. So he found that there were these big spheres of stars. Now, some of them really are in our galaxy. We call them globular clusters. They really are just ball-shaped clusters of stars. But some of them, turns out they're really far away and there are a lot more stars. So He came up with a set of a scale between 0 and 7 for how spherical it is. So 7 is really football shaped, 0 is really spherical. Um, and then he figured out that, of course, with the spirally guys, he has a classification system for those too. Where the 0, S0, is actually edge on. You're looking at it edge on. And then he has the S galaxies, the spiral galaxies, where he's labeled them type A, B, and C, right? And you'll notice that there's the second SB series. What is the SB? Well, this is spiral with a bar, right? Where it's a spiral, but there's this bar running through the middle of it. This is one of the things that's still a mystery about galaxies, is why galaxies have this. There are some hypotheses about it, and we know a decent amount of the actual structure of what's going on here, but why it forms is still a bit iffy. And so he has SBA, SBB, and SBC, right, for the different kinds of spiral galaxies. And then he has this class over here called irregular. As it turns out, there are irregular galaxies as well. So let's look at some examples of these types of galaxies. Well, for an elliptical galaxy, let's go with Messier 85, I think. Well, it's bringing up anything that has Messier in it. I'm gonna try doing this as actual Wikipedia art. Wikipedia instead of Wikipedia. Alright. Messier 85. Here we go. I'm trying to find the one. If anyone knows, put it in the comments. What's the one where they took a picture of the they took a picture of the black hole in the middle of one? Emily asked the question, how do they know they are spheres and not just disks from a different angle? So that is a really good question. How do we know that the spherical galaxies truly are spherical and not just a face-on disk? And there is a way to tell. Generally speaking, the flat galaxies have a spiral pattern to them. So when we do view them face-on, we see the spiral. There are some galaxies that don't have as strong of a spiral pattern, but there's a way to tell the difference if it's just a disk that we're looking at face on or if it's a sphere. And when I bring up a good example, I'll show you what I mean. I can't remember the one where they got that picture of the black hole, so I'm just going to go with, is it 87? It's 87. Found it, guys. Okay. 87 is a really good example of what an elliptical galaxy looks like, which is to say difficult to tell what's going on. So it just sort of looks like a big glowy patch, but this is a spherical shaped galaxy. Now, part of the reason we know it's shaped like a sphere and it's not just a disk that we're looking at from the front is that now that we got a really good look at it, we can see that it's more like a glowing orb, right? The stars are really concentrated in the middle and less concentrated towards the outside. This kind of looks like what we would expect if the density were increasing from the middle outward, and you look at it from any given angle, and it's going to look like this. And then I'm still going to keep coming back to that question because there's more ways that we know, right? So this is what an elliptical galaxy looks like, and this one's a really good example of a very, very spherical elliptical galaxy. As far as this blue thing, by the way, that's something we can talk about if you guys are interested. Now, to give an example of what Emily was talking about, I'm going to look up a lenticular galaxy. So this is not an elliptical galaxy. This is a somewhat flat disk looked at face on. And in the early days, these actually did confuse a lot of people. There were a lot of lenticular galaxies that were misidentified as spiral galaxies. The giveaway on this one is you see how this dust is forming these spirally shapes. So you could tell there's a disk structure there, even if the stars themselves don't make it terribly obvious. This is a particularly challenging lenticular galaxy. A lot of them look more like this guy, right? Where you can kind of see there's a bit of a ring thing going on here. There's a way that you can tell that it's not just, that this actually is a flat disk, whereas the other one's not. I know that's kind of a vague answer. I'm always try to also be honest about things that I don't know, and I will admit that my knowledge of how they go about determining whether it's a lenticular, this one looks really cool, or an actual disc just viewed face, or an actual elliptical, I don't know the finer points of it, so I'll be honest about that. But there is a distinction, and they really can tell. They being, astronomers, professional astronomers, not some guy with a YouTube channel. To give an example, and here's what a lenticular looks like edge on. Right, this is the spindle galaxy. So it truly is a disk. It's just a disk that has this sort of amorphous halo of stars around it. Getting into a spiral galaxy, I guess a really obvious one. Let's take a look at the pinwheel galaxy. This is the one that one guy thought he saw rotating. We now know he was mistaken about that. So the pinwheel galaxy is a spiral galaxy. It actually does have a slight bar. Actually is a little bar in here, but for the most part, it's a big swirling spiral of stars. Now, as I'm showing you guys examples of stars, of galaxies, I want you to start paying attention. And if you notice any patterns, put them in the comments. I want to see. I'm curious if you guys will notice something before I get a chance to bring it up. So, just to show you, this is an example of a spiral galaxy. I'll give you a good example of another spiral galaxy, Southern Pinwheel Galaxy. Here we go. Boom. Now, the Southern Pinwheel has a bit more of a bar feature, right? But here we can see all the big spiral arms coming out of it. The Milky Way, we now know, actually has a bar in the middle as well. And so we see there's a lot of stars here in the spiral arm, not so much in between, right? Big spirally arms. We'll take another look at an example of an elliptical galaxy. It helps if I spell elliptical correctly. Right, here goes another elliptical. Right, big, glowy mass of stars there. And then here's another spiral behind it. We get to see two of them in the same picture, so you can kind of see the difference. Let me bring up a barred spiral galaxy. Barred spiral. NGC 1300, is this the guy? Ooh, I like this one. Big bar feature going through the middle, and then the arms coming off, right? Big spirally arms coming off here. There's also something called an irregular galaxy. For example of that, we'll check out the cigar galaxy. So the cigar galaxy is irregular. It doesn't have a particular shape. It's just sort of weirdly shaped. I'm going to take a quick look at the chat. M87 Black Hole has a photo. Yes, M87, excellent. Okay, so has anyone spotted a pattern when we're looking at these galaxies? Let's see if we can figure it out. We'll do a couple more examples. Messier 80. Let's check out. 87 was the one. This was the first one I showed you, elliptical galaxy. Which one is the Great Barred Spiral Galaxy? There's one, they literally call it the Great Barred Spiral Galaxy. Here it is, NGC 1635. I love this thing. I've actually looked at this through a telescope, and you can cleanly see the bar. It's one of the few galaxies you can see detail in an amateur scope. Here we've got, I'm going to let that load here, this nice, neat little bar feature. And what's interesting is it actually has a couple of bars. So here we see this big bar, but if we zoom in, we see there's another bar crossing it here. There is a bit of directionality here, and then there's the main bar feature, and then two big arms coming off, all right? This is a very loose, a very open galaxy. That was another thing that Hubble took into consideration when classifying galaxies, is that some are tightly wound and some are open and loose. If you're just joining us, by the way, because I realize I've been talking for an hour. So James mentions the core. That's one thing we'll talk about as well. So if you're just joining us, welcome to 1,000 Shimmering Lights. This is... I do this every month. Usually I keep it sort of loose and freeform and let the chat questions drive the direction that we're talking. But because this is the Galaxy Season special, which here at the 1 hour mark, I'm going to go into what Galaxy Season is, because that's the theme of tonight. We're talking all about galaxies. Tonight's just the Galaxy show, man. I could probably talk about galaxies for 4 hours. I probably need to trim the fat a little bit tonight, or I'll run out of time. Okay, so nobody has pointed it out yet, so I'm going to point it out. Have you guys noticed a color difference between the spiral galaxies and the ellipticals? Right? Have you guys noticed that? So all of the spiral galaxies I've been showing have been blue or blue and pink. And all of the elliptical galaxies have been sort of amber colored, right? Spirals are blue, ellipticals. Here's another good example of a spiral, Andromeda galaxy. This is one of the big ones that was the center of that debate, right? This guy, blue, right? Lots of blue, some bits of pink, right? That's what we're usually seeing with these spirals. And right next to it, we got an elliptical, and look, mostly amber colored, right? And this guy out here is sort of a mix. But if I bring up elliptical galaxy, here goes one. This is ESO something something something, right? Sort of amber colored. Why is that? Well, stars live an amount of time depending on how big they are, right? So the bigger the star, the hotter it burns and the bluer it burns, and the shorter its lifespan. The smaller the star, the redder it is and the longer its lifespan. So, if we look at a galaxy and it looks very blue, that tells us it has a lot of blue stars, which tells us it has a lot of young stars, which tells us, because blue stars, they die young, right? They don't live very long. And what that tells us is that new stars are being made in that galaxy, right? Because a galaxy has to replace its supply of blue stars. They die quickly. They don't last very long. When I say they die quickly, I mean in the millions of years, but quickly as far as stars go. Ones that are closer to the yellow and the red ends of the spectrum last a lot longer, especially the little small red guys, the little red dwarfs. So when we look at elliptical galaxies, they're not blue, right? All the blue stars in that galaxy have died. They all popped, right? All that's left are reddish and yellowish stars that are outlasting the blue guys that were born, live fast, die young, rock and roll, whatever, live hard, boom, they're gone. And they've left behind the yellow and amber stars, which is a hint that maybe the elliptical galaxies are older than the spiral galaxies. Now, this is where we're going to get a little bit into hypothetical territory, because this hasn't been completely definitively settled. But there are hypotheses about the way that galaxies form and evolve over time that suggest that because elliptical galaxies seem to look old and spiral galaxies look young, that may represent a true progression. That when they start off, they're big spiral shapes, and then through collisions with other galaxies, maybe gravitational interaction, maybe the mutual gravitational pull of the individual stars perturbing their orbits until chaos eventually results in a blob sphere shape, that the progression of galaxies is to wind up as spherical galaxies. Now, there's another hypothesis that's actually the opposite way, that says that spherical galaxies tend to collide and that the collision causes the stars to swirl around and they settle into a spiral pattern, and it also triggers star formation. So it could be the other way. I personally favor the hypothesis that the elliptical galaxies are the natural end state of galaxies, that spirals eventually become ellipticals. But again, I will admit my ignorance in the topic. I don't know nearly enough to do it justice, and it is still a debate. So it's just like Shapley and Curtis couldn't decide whether those were nebulae or galaxies. Now we can't decide if ellipticals are babies or old men, right? We don't know which end of the spectrum they're on. I think a lot of people are starting to favor that elliptical galaxies are older, but I want to be careful not to say things if I don't know for sure that they're accurate. But I did think I did want to think it would be cool to point that out, and talk a little bit about that. So looks like Jim retracted his message. And I did promise you I'd talk about the galaxy rotation problem, so we will talk about that. And then it looks like Cooper and Karen are saying difference in star formation, red dwarfs live longer, maybe different kinds of galaxies have a tendency to make different kinds of stars. That's not a terrible hypothesis either. It could be that there's something about elliptical galaxies just tends not to produce the blue stars, Maybe that's not because they're old. Maybe the blue stars just have a tendency not to be there. And there's a similar thing going on with the globular clusters I mentioned before as well, where there's a bit of a debate about them because they tend to not have blue stars in them, but then some do, right? So there are things in astronomy that we're still figuring out that are at the edges of our understanding. So I'm going to talk about Jim's original point that he has been very patiently waiting on me to get to. And when I'm talking about the galaxy rotation problem, I'm also going to check Facebook real fast and just see if anyone's messaged me there. Okay, cool. All right, so what's the galaxy rotation problem? So the stars of a galaxy are all orbiting the center, right? And we'll talk about what's at the center as well. Gosh, there's so many things about galaxies. I could go on forever. So they're all rotating, they're all orbiting around the center of the galaxy, and we know that the force that drives things to orbit other things in space is gravity, right? The moon is held in orbit around the Earth because of gravity, and so on. So, let me get a sip real fast. I've had a sore throat all day, so the tea is kind of helping. Okay, so if that's the case, then we understand how orbital mechanics work. We know how fast one thing should orbit another at a particular distance, etc. That's how we're able to put a satellite in orbit and make sure that satellite is the right distance from the Earth by adjusting its orbital speed. But when we look at galaxies and we look at how fast the stars at the edge of the galaxy are orbiting the center, it doesn't work. It doesn't match our understanding of gravity. Because you would think that the stars in the middle of the galaxy would be orbiting really quickly, and the stars further out would be orbiting much more slowly. And you would think that that would create the spiral shape. That would make sense, right? That the spiral shape results from that difference. But observing some galaxies over very long periods of time have allowed astronomers to actually see the stars move every so slightly and then calculate their speeds. And it's wrong. It seems that the stars out near the edge are moving even faster than the stars in the middle, such that the spiral is actually spiraling the other way, right? And so that's weird. Why are the stars near the edge orbiting so quickly? And you can sort of like work out the math and figure out that there should be way more matter there driving this orbit than we see. And this is where we get the concept of dark matter from. Dark matter, a lot of people ask about dark matter because it has a really cool, spooky sounding name. I'm not going to lie, it's awesome. It sounds like the kind of thing you'd write for a sci-fi novel, the ship's weapons are powered by dark matter. But really, we just call it dark because it doesn't glow. Right? Dark matter could honestly be anything. It's dark because it doesn't make itself seen in the visible spectrum, right? It's not glowing, light apparently passes through it, or it's tenuous enough that we don't see it. And so we don't see it here on Earth, right? We don't see it in the nebulae in our own galaxy. We're not finding big clouds of this stuff where we go, oh, that's where all the material is. It's effectively invisible to us, hence dark. I think people would be a lot less apt to let their imaginations run wild if we just called it non-baryonic matter, because it's not made of baryons, but dark matter is the term, and it sounds kind of cool, so that's what we have. So it seems that there is a lot of matter in this universe generating gravitational attraction that we just have no way of directly observing. We can observe its effects, but we can't see it directly. And there's different hypotheses as to what it could be, right? Is it just a bunch of neutrinos? Is it something called WIMPs, these weakly interacting massive particles? We really don't know. There's been a lot of science done to try and see if we can detect them, detect any kind of particles that could account for this extra matter. The science is ongoing. There's even some people that have proposed that maybe it's actually just that our understanding of gravity is flawed, and with a better understanding of gravity, the problem will actually go away and there is no extra matter. But that's considered fringe. The scientific community, by and large, are pretty much convinced that no, there really is this extra matter, and there's a reason why. Again, it's not just closed-mindedness. It has to do with the fact that we actually have a really robust understanding of how gravity works. And a lot of what we know would have to be wrong for dark matter not to exist. Um, and that's hard for me to say because personally I find it difficult. I think, are you sure we're not just getting the math wrong? But especially as a science educator, I kind of have to go where the evidence is, and it does seem like there really is just a ton of stuff in the universe we can't see. I guess that's what it is. Um, and there's even the hypothesis that galaxies might even form in the first place because they're actually forming on clumps of dark matter. That if you take all the dark matter in the universe, that there's areas where it's more concentrated, and that makes the galaxy form. That the galaxy, the baryonic matter that we see, the stars and the gas clouds and stuff, are not actually the driving force for the galaxy to form, but that the galaxy is actually forming around a clump of dark matter, and that's actually the driving force behind galaxy formation. It's kind of an interesting subject, and it does lean into a little bit of what I'm going to talk about a bit later. Still watching the chat to see if there's any kind of questions or anything about galaxies. Don't feel like you're going to throw me off my thing if you ask about galaxies. I know it seems like I have not stopped talking in the last hour, but I happily will address questions as they come up as well. And definitely in future sessions of these live streams, they tend to be a lot less structured than this. They tend to be more free flow. And so I don't want people to forget that. Okay, I'm going to put away my visual aids for now and bring up Stellarium Web. You guys were probably wondering, those of you who have watched the show before, how long it was going to be before I went to Stellarium Web. Because this is the planetarium software I usually use as the driving thing in this show, right? So, we're going to talk a little bit about finding galaxies in the sky. We're going to talk about something called Galaxy Season, why we have a Galaxy Season, and why I'm even doing the Galaxy Season special in the first place. Because the Galaxy Season is the reason for this special episode. So, while I get ready to launch into that, if you just joined in, Dad, what's up? My dad's here. Awesome. Dad, I don't know if you were here for the whole thing, if you've just shown up. We were talking about Edwin Hubble earlier. Dad's a huge fan of Edwin Hubble. He'll tell you. He used to have Edwin Hubble as his wallpaper on his work computer. And say hi to my dad in the chat. So, let's talk about Galaxy Season. So, when we're looking at the night sky, right, I mentioned the exclusion zone. So, here's the Milky Way overhead, which we know is actually our own galaxy, right? That's our own galaxy. Well, if I zoom in a lot here in Stellarium Web, we can start to see more individual objects. NGC 1788, what is it? Cosmic Bat Nebula? Okay, I'm looking that up later. I've never heard of that. You discover all kinds of cool stuff, man. You just poke around in here. Stellarium Web, by the way, is the software I use. This is actually web-based. Oh, I know. Chrome didn't shut down. We crashed earlier. That definitely happened. This is web-based. It's completely free. There's also a downloadable client that's even better that's free. But for some reason, when I live stream it, doesn't look as good. So you can run it in your browser. You can download it completely free of charge, right? Really cool stuff. Made by and for astronomers. You can use this to plan an observing session, right? Because it will actually show you where these things are in the sky. So this is the winter sky that I'm looking at right now. We've got Orion up here. We've got Taurus, right? Sirius here. Now, if I try to find some galaxies, right, in this piece of sky, let me see if I can find any. Well, this looks like it's probably something. Anytime you see a big oval like this on a star chart, that's a good sign. Nope, the California Nebula. They just happen to have marked it with an oval. I didn't think so, man. I feel like if there was a galaxy that huge next to Taurus, I'd have known about it by now. Let's see here. These are all open clusters. I'm not really seeing any galaxies, but we might have to zoom in a little bit more, right? Let me see if I can pull up the lines and get my bearings here and find any galaxies that I know about. Well, I know there's one down here, right? The Andromeda Galaxy, and I can actually time travel a little bit to bring it back up into the sky. So there goes one, right? The Pinwheel Galaxy I showed you guys earlier is Messier 33. It's over here. So there it is again. Big spirally guy there. Okay. So we've got some galaxies going on, right? Let's see. What else do we have? If I move over a little bit, there's another thing that's going to go viral. We'll come back to this. But move a little bit over here. This is Ursa Major. Zoom in. We've got, right? We got the Whirlpool Galaxy. We've got several galaxies up here. So we got this guy M109 by that star right there, whose name is it Fecta? Fad. Oh, see, it says Fecta over here. It had a different label. Anyway, this I think is the Owl Nebula, but that tells me that nearby we've got this guy 108, right? I mentioned Bode's Nebula earlier, which we now know is actually Bode's Galaxy. Here it is, M81, along with the Cigar Galaxy I mentioned before. Okay, now that's decent. But if I come over here and I'm looking at Leo and Virgo, I'm just going to zoom in. There's one. Let's see here. We're just going to go traveling between Leo and Virgo. And surprisingly, I'm not finding very many. There's actually one right there. Where are they hiding? Here we go. Here we are. Okay. Galaxy, galaxy. There's one. 1, 2, 3, 4, 5, 6, 7, 8. There's a couple down there. Here's several over here. Here's a whole bunch here, right? I move over, boom, boom, boom. We got those two guys. We got all this going on. And then we move over to here, and here we go. Now we're talking boom, 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 boom. All these galaxies. What? What is going on in this piece of sky, right? Why are there so many? Markarian's chain, thank you, please. We have to zoom out a little bit to get it. Yeah, here we go. Boom, 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 boom. Markarian's chain. Look at all these. Every one of these blue circles is a galaxy. Every one of them. What is happening in this piece of sky, right? And it tells us where the chain is. Okay, this gets into why we even have a galaxy season. So just like how stars can form star clusters, like the Pleiades I mentioned earlier, right? We'll move over and we'll take a quick look at the Pleiades. Where did it go? Be glad I muted it. That can be loud. Okay. So the Pleiades here, all these stars form a cluster. They actually do live by each other in space. Well, it turns out that galaxies also do this. And it happens to be that there is a cluster of galaxies in this piece of space that we call the Virgo cluster. And in fact, there are many galaxy clusters. There's one over here called the Coma cluster because it's in Coma Berenices. There's a weak galaxy cluster over here in Ursa Major. I say weak just because it's nowhere near like the Virgo cluster. There's a couple of clusters of galaxies in Leo. I think there's one like back here and one up here. They're not actually in those constellations. Those constellations are stars that are part of our own galaxy, but we say that they're in them in that we look through that area to find the cluster. So if I bring up my pictures again, we're going to talk a little bit about the Virgo cluster, right? The Virgo cluster. Or as some of us in the astronomy club like to call it, the Virgo clutter. All right, so here's somebody's picture. Every blurry thing in this picture is a galaxy. Nearby stars have been covered up so they don't distract because they're pretty bright. This is the Markarian's chain I was talking about. Look how many galaxies. So galaxies are not evenly distributed throughout the universe. They're in clumps, right? Again, maybe the dark matter is in clumps and the dark matter causes galaxy formation, so that's why the galaxies are in clumps, right? So we tend to find galaxies in groups. And so the galaxy season refers to the time of year. Hey, Matt's on. Awesome. You can chat now. Okay, so Matt, another great friend of mine, he was actually a professor where I went to school, and we keep in touch sometimes and have really cool conversations. All right, so these clumps of galaxies exist in the universe, and so there is a time of year where the Earth happens to be pointed at them, as we can get a good look at them. So if when I just realized with my mouse I signaled at Virgo, but you guys are still looking at the Wikipedia article. Let me pull up the Virgo cluster here. Actually, I'm going to pull up Virgo supercluster. What is a supercluster? Well, if you get a bunch of clusters of galaxies together, you get a supercluster. This is a three-dimensional artist's impression based on data. This is a map based on data of the positions of, honestly, a positively outrageous number of galaxies. So you see every dot in this picture. I want you to know, these aren't stars. Each dot represented in this picture is a galaxy. An entire galaxy. Every one of these dots. See how many dots are clumped together here in Virgo, right? See how there are fewer dots out here. So there are some galaxies kind of out hanging out by themselves, right? We got a few galaxies over here. We've got the Fornax cluster, the Eridanus cluster, Dorado cluster. These are all named after constellations. Ursa Major groups, right? That's by the Big Dipper we were talking about. The Virgo cluster. If I zoom in, this little clump you see here, that's called the local group, or the local galactic group. Galactic group. Another sip of my tea. All right. That's the local galactic group. Those are the galaxies by us. We are one of these dots, right? The Andromeda Galaxy is another one of those dots. The Pinwheel Galaxy, also called the Triangulum Galaxy, also called M33, is one of these dots, right? The Magellanic Clouds, which are actually a topic. That's another topic, man. I could really go off. The Magellanic Clouds are two sort of irregular shaped galaxies that actually orbit our galaxy, because galaxies will actually orbit each other the way that stars orbit each other and the way that planets orbit stars and moons orbit planets. There are actually big galaxies that have little galaxies that orbit around them. The Andromeda Galaxy does. Those two other galaxies I showed you are actually in orbit around it. Our own galaxy has the Magellanic Clouds. And if you go to the southern hemisphere, you see the Milky Way, and then you can see them. They're like detached from the Milky Way. So this is what we're looking at. And so as we orbit the sun inside of one of these dots, our nighttime perspective changes throughout the year, right? We go around the sun. We can only ever look away from the sun. And it happens to be that around the time of June, July, we are looking this way towards all of these galaxies. And in the winter time or the late summer, we're looking more out to here, right? So if you are and not only are there lots of galaxies, but a lot of the ones that amateur astronomers can see with their telescopes are all here, because you see how we're closer to these than we are to these guys out here. So these are going to be dimmer. These are going to be a lot brighter. We want to look. This is the direction we want to look if we want to look at galaxies through our telescopes. So hence galaxy season. And now I'll take a moment, since we're about an hour and a half into the show, to remind everybody that at the beginning I had briefly mentioned that part of the reason why this Facebook wasn't letting you chat. Part of the reason why I'm even doing this show is as part of a thing called the Galaxy Season Observing Program. I'll actually, you know what, I'll bring it up here for you guys. Okay. And Astronomical League Galaxy Season Challenge. So the Astronomical League is doing this really cool thing called the Galaxy Season. Where is it? Here it is. Astronomical League Galaxy Season Observing Challenge, from March 1st to June 30th, with the deadline for the actual submission of your observations being July 31st. They have a list of galaxies. Here is the list. Hey, look, there's the Cigar Galaxy. There's Bode's Galaxy. There's the Pinwheel Galaxy. There's the Whirlpool Galaxy. Some of the ones we've been talking about tonight, right? What else? Ooh, there's some really good ones in here. Whale, Hockey Stick. Oh, man, we could really... The eyes, that's part of that Markarian's chain I mentioned before. Here's some of the ones in Leo that I mentioned. Where even the Andromeda Galaxy not on this list. They were like, it's too obvious. You got to go for something else. Okay, so wanted to show you guys that real fast. So this thing is going on right now, the Astronomical League. You can get a certificate if you log observations and make sketches of at least 12 of those. And then you'll notice that one of the requirements... where did it go? Or maybe it's up here. Do an outreach activity related to the observing challenge. Hey guys, check. So that's why I decided to do a Galaxy special tonight, because I'm doing this. I will use this as an opportunity to really quickly do another quick plug for the club, and then we'll get back on topic. If you live in the Jacksonville area and you are into astronomy, we are the Northeast Florida Astronomical Society. Our website, if our logo will ever load, is nefas.org, nefas.org. Our members are also members of the Astronomical League and are therefore eligible to participate in their observing programs, although this one specifically, you don't actually need to be an Astronomical League member. So go for it, man. But they do have a lot of other great observing programs, and being a member of our club also involves being a member of the Astronomical League. And club membership, you can go to nefas.org, you can go to membership, join Nefas. You can do new and renew, fill it out, and our memberships are yearly. Students and seniors are $20, individuals are $40, a family is $50. If you just absolutely love us and want to give us extra money just to support us, that is the benefactor level. I always tell everybody you don't get anything different for being a benefactor. Don't just do it because you think you're going to get something cool. It literally just is, some people just want to give more, and that's what that's for. And we have corporate sponsorships as well, and you can advertise in our newsletter. So there we go. I've done my job as membership director and plugged the club. Let's get back to talking about the Virgo cluster and the Virgo supercluster. And I'm actually going to take a quick pause and double check again to see what the chat activity looks like. All right. Got some people laughing in the chat, probably laughing at me doing my sales pitch, but hey, man, I gotta, right? That's my duty. Okay. So that's why we have a Galaxy season. And yeah, Galaxy season happens to be around June, July, that kind of thing. And it is because we're looking towards the middle. You'll notice that it's thickest here around the Virgo cluster, and then there's other clusters, but all of these clusters combined form what we call the Virgo supercluster. Now, one thing you'll notice is that it forms this sort of chain shape, right? This big... So that Markarian's chain that I mentioned, that's literally just in this cluster, but there's this bigger structure, this big long line. And if we zoom out even further... Am I spelling it right? Nope. Okay. Virgo supercluster. What is it a part of? There's a name for it. I was going to try and pull it up. See, Wikipedia used to have... It used to mention it. So the Virgo supercluster is a part of... Oh, right, because I'm looking at Virgo cluster. We move on to Virgo supercluster, and then we find out that the Virgo supercluster is part of something called the Pisces-Cetus supercluster complex. So now if I'm looking at this picture, see this little thing that says Virgo? That little Virgo in the middle? That is this entire chart, right? Now that entire chart is just this little bit in the middle. And you see how we get the little filaments and these big long chains, and every one of these Shapley supercluster. Hey, it's named after the guy that thought the whole universe was the Milky Way. Joke's on him. We got the Capricornus supercluster. These are all superclusters forming even larger structures. Look at this thing. Oh, man. How would you like to live there? Your whole night sky would be nothing but galaxies. This is sort of getting into the large-scale structure of the universe, where we see that there are these sort of long chains and strings of galaxies. And this is another mystery in astronomy. This is another thing we want to figure out. Why aren't the galaxies evenly distributed throughout the universe? Why are they organized into these sort of long chains and filaments? And the current leading hypothesis on this, I would even go so far as to say that it's a theory in the making, um, is that this represents the distribution of dark matter in the universe. That dark matter, for some reason, is not evenly distributed throughout the universe. There are areas where it's more dense and less dense, and it happens to be in this pattern. And so, where there's a high concentration of dark matter, then the material that naturally exists in the universe tends to gather up and form galaxies. Where there's very little dark matter, we don't get much. And you'll notice there's a couple of these areas labeled Capricornus Void, Sculptor Void, Boötes Void. If you like to go to the creepy part of YouTube, like I sometimes like to do, you'll sometimes hear people talk about Boötes Void, and they're like, "Oh, the Boötes Void, it's this vast nothingness," and what it literally it's just a place where there's not galaxies. It's just a gap. It's nothing super special. It was creepy when astronomers first discovered that for some reason there's this huge chunk of this huge zone where, in the constellation Boötes, where there's just nothing. But it really is just a gap in this web, right? Also, there's a popular image of the Boötes Void. In fact, if I Google it real fast, I keep doing that. I keep thinking if I hit G, it's going to fill in Google. Because it normally does. Boötes Void. If I search it, I guarantee you this picture right here, man. First of all, okay, it's literally a couple of boots. You'll often see this, but as this thumbnail points out, that's wrong. This is not actually the Boötes Void. What this actually is it's a piece of gas and dust in our own Milky Way that's blocking some of the starlight from behind it, so it looks like a hole. But there's actually something there. That's what you're seeing here. It's a clump. So not actually the Boötes Void. So if you look up Boötes Void, you'll often see that picture, and that's not true. All right, so I'm gonna take another pause to check the chat here and see what people are saying. Okay, and actually, I think I'll take a quick second to just look at our viewer count. Okay, we've dropped off a little bit. I think we hit 20 viewers at one point. That's awesome. I love it. Obviously, some people drop off. Not everyone can stay the whole 2 hours, but man, every one of you guys that's staying with me tonight, I love every one of you guys, man. I really appreciate you all being here. But I wanted to mention that the last time I did the live stream, I got about to this mark and I said something about how I wasn't feeling well, and I just sort of abruptly ended it. Just in case anybody was worried about me when that happened, I'm fine. I'm not going to get into the specifics. It's my own personal business. But the bottom line is I wasn't feeling well. I really wasn't feeling well. And I actually went to the hospital, had a bunch of tests run, and basically it came back just negative across the board for all the scary stuff. And it turned out that I was just deficient in vitamin and had a panic attack with it because I thought that it was something worse. And that's really all it was. So in case anybody was worried about me, it was nothing, and that's all I'm going to say on the matter because it's just, like I said, it's just my own business. But I just don't want you guys to worry. So there you go. All right. Still watching the chat. Again, I know that there's a bit of a time delay, so it may take a second for you guys to start asking questions or commenting. But let's get back into the fun astronomy talk. So, okay, I said I was going to put a pin in something, and now I can't remember what I put a pin in. What should I talk about next? Oh, I know what I'll do. I'll talk about our own Milky Way, because we're talking about galaxies and seasons. Let's talk about the seasons and our own galaxy. This is something I pretty much talk about, I think, every live stream. I think I always bring it up. If I go back and watch all my live streams, I think it makes an appearance in just about every one of them. So, got a stretch there. I've been kind of hunched. So, I always mention this, but it's just because I think it's really neat, and I think people are always interested in hearing it. Because one of the questions I often get from people is they say, I want to see the Milky Way. Which I think is great. I think every single human being needs to see the Milky Way. At some point in your life, get somewhere dark and look up and see the Milky Way. You owe it to yourself as a human. And this is where I'm going to get a little bit on my soapbox. This is something else I like to talk about, that I actually do feel really strongly about light pollution. light pollution is basically all the light from our homes, our street lights, all that stuff. It all goes up into the sky, and then the little droplets of moisture and stuff in the sky reflect it back at us, and it makes the whole sky gray, right? Or on like really bad cases, orangish, because a lot of that light is orange, and it makes it so that the faint, tenuous, subtle details of the night sky don't get through. And so when we look up, we see a couple of scattered stars, and we don't see the true beauty of the sky that's there. And it makes me a little bit angry because the sky doesn't belong to any one person. That sky belongs to all of us, right? We were born on the earth. That is the sky from the earth. That's our sky. And if somebody, hopped your fence, whatever, went to your backyard and started tearing up your lawn, you'd be upset. That's our lawn. That sky belongs to us. That's your birthright as a human, is to see and have that beautiful sky like your ancestors did, right? The ancient Greeks I mentioned before, the Chinese, everybody, right? The whole world, everybody, all of our ancestors could just look up and see this amazing sky. And now I talk to grown adults who have never seen the Milky Way, and it's not their fault. It's because of all this light pollution. So if you have outdoor lights, you like to light up your yard when you're having a party, that's cool. Think about turning that stuff off when you're not using it. Think about maybe getting the kind of lights used. You can get lights that have a little shield over them so that the light is aimed down. Like little things like that make a difference. So that's my soapbox. But if you haven't ever done so yet, get out somewhere dark and look up and observe the Milky Way. Like I said, that Milky Way is your Milky Way. It's my Milky Way. It's all of our Milky Way. And I think it's good for your soul to get out and see the beauty and the hugeness and the majesty that is the universe that you can observe even just by looking at it with your eyes. So I get people that ask me about it a lot, especially because we have an observing location out in the middle of the Osceola State Forest. And people say, oh, I want to go out there. And do you guys see the Milky Way? Oh, buddy, we see the Milky Way out there. But people ask me about it a lot, and I always tell people, try coming in the summertime, because the Milky Way has seasonal changes like anything else. So I'm going to go ahead and bring up, let's see here. First of all, I'm going to check the chat real fast. A comment got held for review because I think the chat thought somebody was saying booty. First of all, I'm glad to know the moderation tools work. Are there any good pictures of the Booty's Void? Not really, because the Booty's Void is basically a big region where there isn't. So nobody's really imaging something not being there, right? So the Booty's Void, unfortunately, we know about just by virtue of statistical analysis. Where are the galaxies concentrated and where they aren't, and you map them out, and the result of that map is the Booty's Void. So Matt, sorry, your phone apparently died. I just read it in the chat. In the constellation Booties, which I'll show you, and always when we do our in-person stuff, and I point this out, I always say I always say it's Booties. And then the kids always laugh, and I go, "Why are you laughing?" I'm just saying that there's a big old booty in the sky. Now they laugh more. I kind of like to kind of egg them on a little bit, but it's a constellation. It's over by Ursa Major, so here it is, Booties. If I time travel, I can bring it up a little bit higher. So basically, in this region of space, if we look at that direction, there's a lower concentration of galaxies than elsewhere. And they call that the Booty's Void. And really all it is, if I go back to my visual accompaniment here, if we map out the superclusters, we find there just is a big gap where there aren't any superclusters, and we call that gap the Booty's Void. Okay, so talking about the Milky Way and seasonal affective disorder impacting the Milky Way. So this is the Stellarium software, and I'm going to set the date to February around midnight, right? It doesn't get much more winter than this. You see how faint the Milky Way looks. And mind you, this image in Stellarium that they're using as a background is an enhanced image. This is a long exposure. If you go and you look naked eye, it's very subtle. If you get out, I've literally taken people out to an observing site before, gone up, looked up and gone, man, we've got a nice clear night. And they've said, yeah, we got this one cloud kind of going across though. And I've gone, oh, that's not a cloud. That's the Milky Way. Right? They literally thought it was a cloud. And what they were seeing is this ethereal glow going across the sky. It was point a telescope at it and you zoom in and it's just absolutely silly with stars. But it is really subtle like that. But if you get out in the summertime, now it looks like this. What's going on here? So the Milky Way in the summer is much brighter, bigger, and it widens. See how it gets wider right here? So remember that the Milky Way is a big, flat, swirling disk of stars, and we're embedded within that disk. Well, if I bring up my visual accompaniment here again, my visual aids, and I go here to this, and I always like to use the Southern Pinwheel Galaxy for, let's do, for my, oh my goodness, okay, Messier. Oh, by the way, this guy who, this musical guy, M83, is actually named after the galaxy. He said in interviews that he chose that name because of the galaxy. But anyway, this is the actual galaxy that I'm talking about. So I'm going to use the Southern Pinwheel Galaxy as a stand-in for the Milky Way. Why? Because we can't leave the Milky Way and look at it from the outside, right? So this is what the Milky Way looks like. It's a big spiral. Now see this star right here? Let's pretend for a moment that that's the sun, right? That's the sun. Well, we're going to orbit around. I'm going to use my magnifying glass to show the Earth orbiting around. In reality, at this scale, you would not see planets at all. But this is just, a representation. Now, as we orbit the sun, we can only look away from the sun, right? Nighttime is the direction away from the sun. Daytime is the sun, right? The sun's in the way. Well, it happens to be that in the wintertime, we're over here on this side looking outward through these last little wisps. And during the summertime, we're here looking inward through all of this, right? And our own galaxy has a core, just like this galaxy does. It's like a big bulge of stars in the core of the Milky Way galaxy. So when we look through here, not only do we see all of these stars, but we see, if we look across, we see suddenly it gets wider for a second. And we're actually seeing that galactic bulge when that happens. So if you could get out in the summer and look up, then you get to see this, the summer Milky Way. It comes right by Sagittarius and Scorpius. In fact, this is where the bulge is. Sagittarius looks like a teapot. I don't know if you ever noticed that. And the spout is pointing right at the galactic core. And then it narrows and gets a little fainter, comes through Cygnus. It looks real nice in Cygnus. And I'm actually going to mention why. And then as we come over here to Cassiopeia and Perseus, you see it almost gives out entirely. This is getting more towards the winter end of the Milky Way, right? So if you want to check out the Milky Way, first of all, I think you should see both. I think you should see summer Milky Way. I think you should see winter Milky Way. I think you should see the Milky Way 1,000 times in your life, right? But if you can only get out and see it once or twice, the summer one is the one you want to see. And you'll notice in the summer Milky Way these dark regions, right? Again, you won't see these colors and stuff. This is a long exposure photograph, but you will see gaps. You'll see gaps in the light, almost as if there's holes in it. But they're not holes. What they are is they're thick clouds of gas and dust blocking the light of the stars behind them, such that we can't see what's behind that gas cloud. Because the reality is there's just as many stars here as there are above and below, but this big clump of gas is obscuring our view of those stars. And it turns out that when we look at other galaxies, see all the little brown smudges in this picture? That's the same stuff. So we can see those in other galaxies. Astronomers call them dust lanes. Although when we talk about dust in astronomy, it's not like the stuff you wipe off your countertop. It's just our term for everything that isn't hydrogen, essentially. Okay. Let's see here. Yeah, what would the booties void look like? A black image. You know what it would look like? It would look like the Battle of Winterfell from Game of Thrones, when nobody could see anything. It was too dark. Um, kids love the butt jokes. They absolutely do. Okay, this is not too off topic, but with the moon bases, do you think we will see lights on the moon like Earth at night in the next century? Probably, right? Um, a century is a long time, man, and I wouldn't put it past us to colonize the moon in the next century and start to have lights. The moon has an advantage that the Earth doesn't have because the moon lacks an atmosphere to bounce that stuff back at us. So actually, light pollution, even with a bunch of lights, wouldn't be as bad on the moon. The problem that the moon has that we don't have is the moon itself is really reflective. So if you're during one of the phases where the sun is pointed at the moon, where you're angled at the sun, the reflection off the lunar surface is going to blind you so much that you won't see the stars. In fact, that's actually why you don't see stars in the Apollo photographs. Is in order to see the stars, they'd have to overexpose the images to the point where the moon is blown out. So they did really short exposure times in all their photos, and the brightness of the moon limited that, and so the stars don't appear in the images. But that is actually a really good question, and my buddy Matt says, I hope so. I hope that what he means is that he hopes we get to the moon in the next century and form a nice big colony. I think it would be really cool. Um, and yeah, that's why, yeah. So I actually like the people that say, I don't, okay. I kind of like when people say, like, oh, we didn't go to the moon and they bring up their points, because if you investigate those points, you get to learn a lot of really cool stuff. Um, that could be another theme video one day. But yeah, the that's actually why you don't see the stars in the photographs. And some of the images from Apollo, people have actually put them into software and like crank the levels, and the stars actually do appear. There are some images where you can bring them out by like I think you have to use the negatives. I'm not sure. I've seen like stuff where people have done that and they've actually managed to pick out some of the stars, which is kind of cool. Um, so yeah, so we talked about the seasonality of the Milky Way. We've got about 13 more minutes left in this live broadcast. Matt says the lunar retroreflectors. Yes, okay. So I talked a lot about galaxies. I definitely think I can justify calling this the galaxy episode. I don't mind getting off topic. The retroreflectors. So retroreflector, if you don't know, is basically you arrange a set of mirrors in such a way that when light comes in and it bounces, it will bounce around and come right back out at the exact same angle it went in. So a flat mirror, light always reflects at the equal incident angle. So if it comes in shallow, it skips off shallow. If it comes in, it comes off. You guys know how a mirror works. A retroreflector doesn't do that. No matter what angle the light comes in, it goes right back out the same angle. And so when they when they went to the moon, they set up a lot of surface experiments. They left behind a lot of experiments on the moon. There were seismic experiments and stuff. And one of the things they did was they put these like boxes that had retroreflectors in them. They had these assemblies of mirrors in them. And to this day, they fire lasers at the moon and bounce off those retroreflectors, and they come back and use that to measure how far away the moon is and get information on the moon's orbit and the rate at which the moon is actually moving away, because it is actually moving away a little bit, and this kind of thing. So it's actually really interesting that not only did we go to the moon, but they left behind mirrors that they still bounce lasers off of today. Also on topic, cat's eyes are sort of like a natural retroreflector. They have a thing called a tapetum lucidum on their retina that bounces light back like a retroreflector, and that's why their eyes look like they glow. A lot of animals have it. That's what the reason why there's eye shine. All right. So, with our remaining... I thought those would not work anymore. Yeah, no, they still do. And, it's interesting because things rarely... there's not a lot of... there's no erosion on the moon. There's no wind on the moon, right? So a lot of the things we've left behind on the moon are pretty much like the day we left them. What there is radiation, right? So some radiation has definitely damaged some of that equipment, but retroreflectors basically just are mirrors. So they're going to be up there and fully functional for quite a while. No problems there. Does anybody have any questions about galaxies? The theme of tonight, like I said, is galaxies. Not that I don't mind getting off topic and talking about some other cool stuff, which we can definitely do, but galaxies is the theme. And actually, I'm pointed at the right thing to be pointed at to talk about something cool. So I think with the last 10 minutes, unless somebody has an interesting question, I'm going to tell a story about, let's see, put in a plug for the Science Festival at Metro Park. Yes, Mike, thank you for the reminder. Mike, I don't know if you were here at the beginning of the session. I did talk about the Science Festival. I'll go ahead and mention it again real fast. Today, sorry, I keep forgetting it's the daytime thing. Today, tomorrow, and the day after at Metro Park, we are going to have solar telescope set up at this thing called the Jacksonville Science Festival. Let me bring this up. So if I go back to our website and I go to our calendar, you know what? Actually, I'm just going to use the last 9 minutes to talk about upcoming events. And then I did have a story I really wanted to tell. Maybe I'll stay a little bit late and tell the story. We'll see. Actually, maybe another time. It's there's a folklore thing about the Milky Way that I think is kind of neat, but it's not a science thing. It's a mythology thing. I think I'll just skip it and save it for another time, unless you guys really want to hear it. So anyway, today, tomorrow, and Saturday is the Jacksonville Science Festival. It's at Metro Park, 1410 Gator Bowl Boulevard, from 9 a.m. to 5 p.m. They're going to have a lot of booths set up with various people talking about various scientific topics, and we will be there as well. I want to remind everybody that under normal circumstances, it is not safe. I want to emphasize, not safe to point a telescope at the sun. The retina of the human eye does not have pain receptors, and the amplified UV radiation focused directly at your retina will blind you like that, and you will not feel it. You think it's going to hurt you a little way? No, you won't notice until it's too late. It is not safe to observe the sun with a telescope. We have special equipment that is specifically designed with special filters that makes it safe to observe the sun, and we will have that, and we'll be observing safety protocols with that equipment, and we'll be supervised the whole time, and we will have that stuff at the Jacksonville Science Festival. So in that controlled environment with our specialized equipment, we will be safely observing solar phenomena such as sunspots and what we call prominences. Those are those sort of loopy guys. I don't know why I'm describing it. I'll show you a picture. We'll be looking at solar prominences as well. Solar prominence. There we go. I can't spell it all. Thank goodness for Google. Okay. So, wow, this is an example of a really big one. But these things coming off the side. These little guys are a little bit more like what we typically see. Man, I would love to see one of those. So those are solar prominences. We're going to be looking at that kind of stuff, sunspots, all that neat stuff at the Jacksonville Science Festival. Again, that is today, tomorrow, and Saturday. I'm thinking about going Saturday. I haven't made up my mind yet because I'm also planning on going to our dark sky location on Saturday, and I may have too much stuff on my plate. But if you do see me there, what's up? The other thing we have coming up, the next big event that I want to talk about real fast is Hannah Park. We do this every month. So we go to Catherine Abbey Hannah Park. And by the way, so for the people who are tuning in that aren't in Jacksonville, sorry, I know this isn't applicable, but this is, always want to shout out our club, of course. We do this. The park charges $5 per car, not per individual. That's the park's entry fee. We don't charge that. We don't charge anything. You have to be in by 7:30 p.m. This time changes throughout the year based on daylight savings. Right now it's 7:30. And this is going to be happening April 9th. We do this every month. We plan it based around the phase of the moon, and there's reasons for that. So this is close to first quarter moon. That means we're going to have enough moon to look at it, but not so much moon we can't see anything else. All right. But if you don't track the lunar phases, just check our calendar. April 9th from 7:30. Basically, it'll start when it gets dark. And then it says till 10 p.m. Honestly, we just hang out until people get bored and leave. Right? I am usually at Hannah like after this thing is ended, still showing people stuff. When no one else is there is when I leave, right? And I do a laser pointer toward the sky. You can actually see the laser into the sky, and I show you the constellations and do stuff kind of like this in person. This was actually inspired by what I do during those events. And then we have a bunch of telescopes. All of our club members, we all bring out telescopes, and none of them are there for us. Those telescopes are there for you guys to look through and enjoy. And that's Hannah Park. I got 5 minutes left. And let me check the chat real fast, see if anything else is going on in the chat. And Mike says he joined a little bit late. Hey, man, I appreciate you being here, and I appreciate you reminding me because I need to remember to do my announcements a few times throughout the show because we do get people who join early and drop off. We get people that join late and stick till the end. So I want to make sure that everybody knows about all of our stuff. All right, I'm going to splurge a little on the last 5 minutes. And if you guys will indulge me, I'm going to tell you guys a story. So this is loosely, and I mean loosely, on the topic of galaxies, because it's a myth about our own galaxy, the Milky Way, and it's a Japanese story, and I absolutely love it. So the story goes that in the court of heaven, that the great emperor of heaven had a daughter, and the daughter's name was Orihime. And I cannot remember which one she is. Let me find out real fast. Sorry, I'm derailing the story already. The Weaver Girl and the Cowherd. Yeah, that's what I'm looking for. She is associated with Vega. Cool. All right. So, this star up here... Oh, hold on, let me get to that right page. This star up here, Vega, represents Orihime in the story. So the story goes that Orihime was the daughter of the great emperor of heaven, and she liked to weave. She would weave cloth, right? Weave like silk, like kimonos and stuff. And the story is that she was really, really good at it, and the great emperor of heaven, I'm going to remove the lines, they're not pertinent to the story, basically loved the cloth that she wove, and she loved that it made him happy, and so she wove cloth all day, every day. That's all she would do, is weave cloth. And she loved it, but... Oh, there's a comet? I'm sorry, I'm getting derailed again, but I might have to take a look at the comet. Anyway, so she would weave cloth all day, every day, and one day she was sad, and the Emperor of Heaven noticed that she was sad and said, "Why are you so sad?" And she said, "Well, because I spent all my time weaving the cloth, I'm never going to meet a man and get married," right? It's a traditional story, traditional values. She's like, I'm never gonna get married because I'm weaving the cloth all day. So the Emperor of Heaven says, well, that won't do. My daughter's sad. So he says, tell you what, take a break, and I'm going to introduce you to somebody. And he introduces her to a celestial cowherd, the great celestial cowherd, whose name is Hikoboshi, and he's represented by the star Altair. And so they meet and they fall madly in love, and they get married, and then they spend all their time together, and they completely neglect their duties. There's no cloth being woven. The cows are running rampant all over the sky, and the Emperor of Heaven, he gets angry and he says, "That's it. No more. You can't see him anymore." So then they're sad. Okay. He goes, fine. You can see him once per year, right? So the story goes that on a special night every year, they have an opportunity that there's a bridge. So the Milky Way in this story, I tell you, the Milky Way is part of the story, is the great celestial river. And there's a bridge across the river. And so once a year, they can get together, they can come together and meet at that bridge. Okay. So the first opportunity to meet comes, and it rains and rains and rains, and the river floods, and it washes over the bridge, and it's not safe to cross. So Orihime is sad again. And the pattern in this story is Orihime is sad and then somebody does something to fix it. But she gets sad again, and all these magpies fly in and they form a bridge over the river, and she walks across the magpies to be with Hikoboshi, right? And so the tradition now is that every year in Japan they have a star festival to celebrate that Orihime and Hikoboshi can meet. And on days when it rains, they say that the rains prevent the magpies from forming the bridge. and it prevents them from meeting each other. And so if it rains on that festival, they call that rain the Tears of Orihime, because they say that she's sad that she can't meet with Hikoboshi. So there we go. I slipped in a little mythology for you guys at the end. And let's see here. Halo has a TV show. I know what to do after this. Okay, cool. After the show, after this presentation, we're watching Halo. Awesome. Well, it's 9 o'clock, and you guys sat through my weird Japanese mythological story. So I really appreciate you guys. I hope you learned a lot about galaxies tonight and are excited for galaxy season. Get out and look at this stuff if you have a telescope. And I will see you guys in a month. Remember, third Thursday of the month? Every month we're doing this. Unless I have to reschedule because it's St. Patrick's Day. Like I forgot this year and I had to reschedule and it threw a lot of people off. Thank you and have a wonderful